I got a bunch of examples here that you guys can start to work on, or we can work on together. I'm gonna start on the first one with us, on the first one together, and I don't know if we can go through all of these, both of these, or there's 3 there, I guess, right? Okay, let's get to work on them. I tell you what, I'm going to give you guys a chance to work on the first one on your own. Okay, I'll give you about 5-10 minutes to work on it, and then I'll go over it. Okay, you have a sample of 100 bottles of detergent, and find that on average, each bottle is sufficient for 57 washing loads. You know, the standard deviation for the entire production of 100,000 bottles is 5 loads per, is 50. That's wrong. That can't be 5. Oh, no, it's 5. That's okay. I'm wrong. You know, standard deviation for the entire production of 100,000 bottles is 5 loads per bottle. So what do we know here? We know that on average, we took a sample of 100 bottles, and our average number of loads that we could do for on those 100 bottles, some of them we did 60 loads, some of them we did 50, and so on and so forth. The average we got out of each bottle, out of those 100 sampled bottles, is 57 loads. That's our sample average, right? So the answer to question A is 57 mu or X bar. It's X bar, right? It's the sample mean. Now 5 is our standard deviation for the entire production of 100,000 bottles. Is that sigma or SD, standard deviation? That's sigma, the population standard deviation. So I'm going to do the next part with you. Oops. Ooh, you know what snuck in there? Oh my goodness. Levi, did you discuss confidence intervals? Just touched on it. Okay. I may change that question, this question, just a little bit. Calculate the range within you'd expect 95% of the sample means. Okay, so I'll leave it up to you to do C and D. I changed D a little bit, right? Okay, calculate the standard deviation for your samples. We give that a special name, by the way. To avoid confusing these two, we have a standard deviation, or sigma, that we have for the population. When we talk about the standard deviation for the sample means, we give that a new name. We call that the standard error of the means, okay, or standard error, just short for standard error. Okay, so that's going to be our sigma over the square root of n. So I'll leave the C and D up to you to calculate. How are you guys doing at home? No response. Guys awake? Oh, good. Okay, thank you, Andy. Okay, so what's our standard error? Okay, Standard deviation, sigma is what for this example? Is 5, right? The sample size is 100, right? So square root of sample size is 10. So what is our standard deviation for the sample means? Is 0.5, right? It's 1/2. Okay. Now, let's think about calculate the range within which you'd expect 95% of the sample means to fall. Okay, well, if we're right about the mean, right, if we're, for a moment, let's assume we're right about the mean, we would expect 90, given the sample size and the population standard deviation, we would expect 95% of the sample means to be 2 standard errors. Remember, now I called it standard errors because we're talking about the sample distribution, the distribution of repeated samples of size 100. I would expect 95% of the results to be between 2 standard deviations below the mean and 2 standard deviation, in our case standard errors, below the mean and 2 above the mean. What's the standard error? It's 0.5, right? So 2 standard errors is 1. So what's our mean? Was 57, right? So at least that's what our sample suggested. So we kind of expect that 95% of results are going to be between 56 and 58 washes, right, for a sample of 100. Okay, what if the sample size had only been 25? Sample size has only been 25, right? What would the standard error have been then? It would have been 1, and 95% of the time we'd expect the results to be for another samples of size 25 between 55 and 59. Okay, 2 standard deviations or standard errors below and 2 above, and since standard error is 1, in that case, as the sample size gets smaller, we're less certain about our samples spread out more. So we're less certain that they approximate the mean very accurately. As our sample gets bigger, we get more certain that they approximate the mean and that they're going to be close to the mean. Okay, now that's interesting. Another way of saying that is we have a level of confidence that 95% of the time these means are going to be within that range, within 2 standard errors below the mean and 2 standard errors above the mean. Well, let's say we only take this sample one time. If I took a sample one time from this population and I didn't know about this, the population, I didn't know about the central limit theorem. I just go to this population. I happen to know that the standard deviation of this population is 5. Fine. I take a sample from this population. I get a mean of 57, right? What do I know now? I know that I took a sample of size 100 and I got a mean of 57. But I just know it's 57. I don't have a good handle on how certain I am it's 57. I don't know whether, just by looking at that mean that I've taken, I don't know that, it could be 52 or 63. How certain it is that it's not as low as 53 or not as high as 67 or 51. I don't have a way to judge how accurately I've determined that mean from that sample size. But knowing the central limit theorem, I know that 95%, if I resample this distribution over and over and over again, I know that it's only going to have, my results are only going to vary by so much based on the sample size and the variability of the population itself, which I know is 5. So now, not only when I look at E, not only, I'll look at E in a second. When I look at the answer to D, not only do I know that the mean of the population is somewhere around 57, I also kind of know that, gee, it's unlikely it's going to be more than 2 standard deviations below that or more than 2 standard errors above that. I can bracket my level of certainty about that mean. So now not only do I know the mean is around 57, but I can also predict that I'm 95% sure not only is it close to 57, but I'm 95% sure that if it's a sample size of 100, that it's somewhere between 56 and 58. If it's a sample size of 25, I'm 95% sure it's between 55 and 59, right? So now not only do I know approximately where the mean is, but I know what level of certainty that I have that it's within a certain range. And in statistics, we love 95% certainty. We don't mind anything about 5% error. 5% error is nothing. We ignore 5% error like it's meaningless, right? To put it into perspective, I think I probably mentioned this before. In CERN, where they're doing this experiment with that super large collider that they have, and they're trying to predict whether they find this particular particle. The level of certainty, it's also, they have to do the appearance of this particle is very irregular. So they have to decide whether or not they really see it statistically. And they demand of themselves, before they announced that they think they discovered it, this boson, before they announced the Higgs boson, I guess it is, before they actually announced that they've discovered it, their demand for themselves that statistically that they be certain with at the level of 6 standard deviations, right? That's like 99.99999% certainty, right? Well, we don't have, $5 billion to build a 4-mile linear accelerator, right? So most studies, we're doing on a shoe budget, right? So most studies, the level of error that we're willing to accept is often around 5%. Another way of saying that is that we're satisfied with a 95% level of certainty. We're 95% certain of something. Okay, so now we're, based on this sample of size, let's say the smaller sample size, 25, we're 95% certain that the true mean for this population, the place where we have 95% of these samples, means if we kept redoing it, and also the mean, we'd also capture the population mean, is between 55 and 59. So if I told you that another company, I'm going to change that from 95 to 62. If I told you that another company is known to make a product that washes 62 loads, so on and so forth, we know that for a fact, would you say that the two of them are different? Well, we're 95% certain that our material only washes from 55 to 58. So if this other one does 62 loads, we're 95% sure that they're different, right? Because that's outside of the range of uncertainty that we have for our real population mean. Okay, now, if I had asked you that they make a product that washes 58 loads and our average was 57, could I say with 95% certainty that they're different now? No, because it's within the range of my level of certainty. In other words, I can't say it's outside of the range that I would expect 95% probability that where my real mean is. Okay, that's what we call a confidence interval. Okay. Next week, we're going to be really getting more into this idea of confidence interval, calculating it more frequently. Okay, let's see what we got next. We talked about proportions, right? Well, we have the same deal going on with proportions, okay? Except with a proportion, we also predict a distribution for our proportion. For instance, when we talk about a proportion, we're talking about, let's say, half of the company, let's say I'm going to flip a coin 1,000 times. We would expect to get 50% of the time, we'd expect to get heads, right? So now, we're not going to get heads. If we flip it 1,000 times, we're not going to get heads 500 times, right? That would be a relatively rare occurrence to get exactly 500. We're going to get close to 500, but we're not going to get exactly 500 very frequently, right? But we're going to get 499 sometimes, and we're going to get 501 sometimes. We're going to get 498 heads sometimes, 502 sometimes. As I get further and further away from 50% heads, 500 heads, it gets less and less likely that I would get a result that extreme. Not very likely I'm going to get 300 heads. Very unlikely, as a matter of fact. I'll get 300. Very unlikely I'm going to get 700 heads if I flip a coin 1,000 times, right? Because that's a really big sample, okay? If I took a smaller sample, well, things happen, right? If I took a sample of 10, well, then it wouldn't be that unlikely I'd only get 2 heads or 8 heads, and so on and so forth. Those are sample sizes. Our proportion, if we repeatedly sample a proportion, if we repeatedly flip that coin 10 times and make a distribution, make up a histogram and a bar graph, a histogram based on our results, it's also going to be approximately normally distributed. Okay, but now the width of that is determined by the sample size and the probability that we're dealing with. So you guys may have noticed that we made, when we were talking about the distribution of samples from involving a proportion, we said that the standard error there, the distribution for those repeated samples, is equal to the square root of the probability of getting a certain outcome times 1 minus the probability of that outcome over the sample size, the square root of that whole thing. Okay, that's going to represent our standard error for proportions. So where might we apply something like that? Okay, if I were to suggest to you, let's take a look. Suppose we know the true population proportions of Americans who are willing to accept the cut in living standards to help the environment. In 2010, the General Social Survey asked random samples of questions of Americans how willing were to accept the cut in living standards to help the environment. Out of 1,381 respondents, that's our sample size, right? 496 said that they were very willing or fairly willing. Okay, what can we say about P? What's our proportion of people that are willing to accept that cut? Okay, what's our p-value? What's our proportion? Right, it's going to be 496 out of 1,300. I'm going to open up Excel to make this a little bit simpler. Let me move this out of the way. Okay. And let me spread this out a little bit. Okay, so let's see. Our proportion is going to be equal to, move this over so I can read it. It is equal to, where is it? 496 divided by 1381. Okay, about 36% of the people in the United States, 36% of the people in our sample, right, agree with that statement, right? Is that what the entire American population agrees with, though? No, we don't know what the entire population says, right? So now we know we took a sample. Our sample size was 1,391 people. Nice big sample. Okay, so now this is P. Sometimes we call this P cap, okay, because it's a sample proportion. It's not the population proportion. Okay, so now, and by P cap, I just put cap. I really mean like a P with a little cap on top of it, a little caret on top of it. But I'm calling it P cap because I can't do that very easily right now. Okay, so now it's nice to know that the proportion in our random sample of 1,381 Americans is 36% roughly. But we also want to know what's our level of certainty with this. Can we say that the majority of people don't support this based on this result? Okay, so what do we need to know then? We need to know how likely is it that we got this result if the population proportion was really 50%, right? Or more than 50%. Well, we need to bracket this again, just like we did before. We need to get an interval in which we know that the likelihood is 95% that we would include the actual mean, the actual proportion of the entire population. So in order to do that, I need to know what the standard error is for this distribution, how spread out this distribution is. So in this case, we're going to say it's equal to the square root, parentheses, of p. What's p? 0.395, I'm going to make it 0.36, make it simpler, times 1 minus p, which is 0.64, over the sample size, which is 1,391. Okay, and I don't think I have to use parentheses here because I think they're all the same level. And I'm going to hit enter. And our standard error is 0.013. Okay, that's a proportion, our standard error, right? In other words, if I'm going to draw the entire distribution of all the possible samples of this size in a normal distribution, that would be what represented our standard deviation or standard error, really, because it's a sample for this entire population. So when we want to look at 95% of the possible outcomes around that, what we think is the middle of this range, right? Well, we need to look at 2 standard deviations below our proportion and 2 standard deviations above. So how am I going to do that? I'm going to say 0.359 plus 2 times this value. Okay, I'm going to put that in parentheses if I can. And I'm going to look at the same thing below. It's equal to 0.359 minus 2 times our standard error. So not only did our sample tell us that we think that the population, that the proportion of the people in population that are in favor of this question is 0.359, but also that we're 95% certain that the true population proportion is between 0.333 and 0.385. Okay? So we can do the same thing with a proportion that we did with a sample mean. We can bracket it and have it so that we can tell what our level of certainty is when we take a survey that involves a proportion. Anytime you ask a question that's a yes or a no, does the person in this population have diabetes or not have diabetes? Are they positive for Ebola or not positive for Ebola? Right? Anytime you take a sample that involves a binomial or a possibility of 2 values, you have a proportion. And a lot of stuff that we're doing involves proportions. Okay, so, yes?
So that has a sampling distribution.
Right.
The proportion, because you can calculate a standard error.
Right.
And that standard error just depends on the proportion that you measure in the sample size.
It's the proportion we measured and the sample size, right? So in other words, here, let me draw it.
So in the population, there is no distribution for that. There's just a proportion.
There's just a known proportion, right? Because the population just has a proportion. Same thing with the mean.
There's no standard deviation.
Same thing with the mean. The mean has no spread. The mean is the mean, right? We never know what the mean is, right? We never find out what the mean is. But the mean has no, the mean is a single number. It's a value that exists, right? So this is a distribution of what happens if we took these samples over and over and over again. Half the times we're going to be below what the real proportion is. Half the time we're going to be above what the real proportion is. And what we're doing is we're looking at our distribution of all the possible outcomes that we can get for this value for the proportion, which we measured first time as 0.3, what was it? 359? right? So if I repeat a sample of 1,396 people, I may be below that or I may be above that, right? And depending on what the proportion is and how big the sample size is, that'll tell me what this spread is. And it'll also tell me what the probability is that we've captured the mean within this certain range. Okay, so that's really what I'm looking at here. I'm really looking to learn about sample distributions, whether they involve an actual number, whether they're a numeric variable, right, like blood pressure, right, or whether they're a proportion, like the percentage of people that are immune or have a disease or something like that, right? So I'm treating them both the same way. What I really want to know about them is, number one, what the true population proportion is, right? Or I'm never going to know that unless I actually count it, but I want to infer it from my sample proportion, right? My p cap, and basically I know that this is going to approximate my proportion, but since I can't ever know that I've actually gotten the proportion, the next best thing is to know, well, what range do I have that I'm 95% sure that this population proportion is really falling within. Same thing with the mean. Okay, I can't ever know what the mean is, but I can use X bar, my mean and my sample, to infer what the mean is, and I can also know that what's the level of certainty that I have that the real mean is within a certain range of what my sample mean was. Okay, so that's what I'm going to do now. Instead of worrying about trying to guess the real mean, which I can never know anyway, I'm going to be satisfied with knowing how certain I am that the real mean is within a certain range of the sample the sample results that I've got. Okay. Okay. So let's see if we. Yes.
Proportions will be not just for the two options, but anything that has more than one option. So anytime you're kind of separating the population into groups.
Yeah, categories, right? Right, because that's really what that is, a categorical variable, right? Male or female, proportion to male or female, proportion of Hispanics in the population, 15% Hispanics. If we took random sample of all people in New York, randomly sampled 20 people from each borough, 100 people, by some sort of phone records or something like that, and we found 15 of them were Hispanic. Well, our P cap is that 15% of the population is Hispanic. Is that true? Well, probably not. It's probably not exactly 15% just because our sample was 15%. But at least now we have a mechanism for saying, well, our sample came out 15%. And since it was a random sample and the proportion is 0.15, I can kind of now know what the range is for 95% certainty of what the real proportion is, right? So that what would we do? We take our how do we get that again? 0.15 times 0.85 over 100, the sample size. Take square root of that and take two standard deviations below the 0.15 and two above. And now we've kind of bracketed or predicted that the true population proportion of Hispanics is between these two numbers. Okay, so this is valuable. Now we got a mechanism for taking a sample and understanding how accurate it is. Okay, and how we compare it to something else. Okay, that's really important now too, because say we're going to do studies involving the efficacy of a drug. Okay, does a drug really lower blood pressure? So you have a control group, you have a experimental group, right? And you look at the averages for how much it lowered blood pressure in each one of the two groups. Well, this one blood pressure for the placebo group was 80, and the blood pressure for the other group was 74. Are those two numbers far enough apart so that you really know the two means of the two groups are different enough to say with 95% certainty that the results, the differences due to a real difference in the performance of the drug, or is it due to just chance that, because if you took two averages of any population, took a sample of any population, you're always going to get one number that's higher than the other. Now, is that difference due to chance, or is it a real difference in the two populations? Okay, so let's try next one. Okay, high efficiency washing machines use less water and less detergent than standard washing machines. Everyone varies the amount of detergent they put in. I don't know why I did two like detergent things here. I must have been doing the laundry or something. Interesting. But at any rate, I didn't realize I had done that. Everyone varies in the amount of detergent they put in washing machines. Some people put a little in, others use more. How many loads does a full 150-ounce bottle handle on average? The results of the number of loads watched represent 10 randomly selected users. Okay, so now these are 10 people that reported how many washes they got out of the same bottle of detergent solution. Okay, so now, first of all, we need to have a random sample, right? This is a result of 10 randomly selected users. So that's one of the assumptions that we satisfied. There's another issue, the sample size and stuff like that. For this week, I'm going to ignore the issue with the sample size. Calculate the mean number of loads per bottle. Okay, well, how are we going to do that? We're actually just going to add these up, and we're going to take the average for all of these bottles. Then we're going to calculate the standard deviation. Now notice that I didn't do this for everybody that washes stuff, right? I only did this for 10 people. So what have I not given you here? I haven't given you the standard deviation for the number of loads that the entire population gets out of this. So we're stuck in we can calculate the mean for the sample just by adding up these 10 numbers and dividing by 10, right? But I don't have a standard deviation for the population. So where am I going to get my standard deviation? Well, if you take a random sample, right, that random sample is going to approximate the mean of the population, right? You randomly select 10 people, and some people are going to be under the mean, some people above the mean. Bigger the sample, the better the approximation, but you're going to expect your average for those 10 people. Somehow it's going to approximate the mean. Well, now, the spread is also going to mimic the population. In other words, these numbers, since they're random, are going to kind of reflect what the spread of numbers in the population use of this detergent are. So I can actually use the standard deviation of this population to represent of this sample to represent the standard deviation for the entire population. So I'm going to put in these 10 numbers into Excel. You guys can do it also if you want. 87, 88, 103, 98, 94, 99, 89, 91, 87, 91. Okay, so the average is, okay, guys got the same as I did, 93 is the average, roughly. And the standard deviation of the sample, right, not the population, the sample, is 5.6. Okay, this is X bar, right? Sample, it's not population mean, it's the sample mean. And this is the standard deviation, not sigma, right? Standard deviation is a sample. When we were working with the central limit theorem a few moments ago, one of the rules that we had was we had to know the population standard deviation, right? Because if we looked at it now, instead of having one element of uncertainty, the mean, now we have two elements of uncertainty. we're guessing at the population standard deviation, and we're guessing at the mean. Okay? So now that's a problem for us. So we need another tool. Next week we're getting kind of a preview on what we're going to get into next week and the week after. We need another mechanism for predicting what the likely spread is for a sample of this size from this population. If I ignored the fact that this was the sample mean and just said, oh, it's the population mean instead, right? Well, then where would I expect 95% of my outcomes to be for these repeated samples? Or within what range would I expect my population mean to be? Well, I would expect it to be 93, right? Plus or minus, right? I added or subtracted 2 standard deviations above the mean and 2 standard deviations below the mean. Okay, so I'm going to say equals 93, right? Well, let's see. The standard error that I'm dealing with here. What would the standard error be here if this were indeed, if we really got lucky and we guessed the population standard deviation exactly right? What would my standard error be? It's going to be equal to square root of 5.6 over, excuse me, 5.6. Yes, thank you. I appreciate it. Over the square root of the sample size, which is 10, right? Sample size 10? Yep. Okay, it's 1.77. That's my standard error. That's how much I would, given that this is our approximation of the mean, I would expect the population to have a spread, a standard deviation of about 5.6, similar to what my sample did. I would expect, if repeated samples of size 10, to have a spread or standard error of 1.77 because they're a larger sample size than, like individuals in the mean, in the population. So now, where would I expect 95% of these results to occur? Well, I'd expect them to be within 2 standard deviations below the mean and 2 standard deviations above the mean. So that's going to be equal to 93 minus 2 times 1.77, or 89.16, or 93 plus 2 times 1.77, or 96.24. There's 2 cheats there that I just did. One cheat is that, I'm going to look at this formula again, equals 96 minus 2 times the standard error. First cheat I did was I used the empirical formula. I didn't actually look the z-score up. Anybody here know what the z-score really is for 95% between? It's not really 2, it's really 1.96. That's the first cheat, right? I use the empirical formula instead of the real z-score. If you look up the table for 97.5% on this side and 2.5% on this side, and 95% in between, it's really negative 1.96 standard deviation, positive 1.96 standard deviations. That's one cheat. The other cheat I did was I used in order to calculate standard error, I used my sample standard deviation instead of knowing the population standard deviation, right? So I have to accommodate for that extra level of uncertainty. If I don't accommodate for that extra level of uncertainty, well then I'm saying I'm 95% certain, but I really am not, right? So instead of the range, instead of the range being 89 to 96, I need that range to be wider, right? The wider I make that range, the more confident I am that the real mean is between those 2 numbers. That's going to come up next week. Okay, so I need this to be wider. So my cheat here is inappropriate. Next week and the week after, we're going to be working with something new that's going to be a z-score that's adjusted for the sample size, for the level of uncertainty that's added in by the sample size when we use the sample to calculate the standard deviation. That's called, instead of a z-score, that's called a t-score. And that's based on the sample size. The smaller the sample size, instead of using 1.96, we use a larger number than 1.96. So the spread is wider, and it accommodates for that extra error. So, make a long story short, today we looked at populations, the way that they're distributed. We took a quick look at them from just repeated what we've done before with predicting what proportion of a population is less than a certain number, more than a certain number, based on the mean and the standard deviation of the population if we know them. Then we looked at how samples behave instead. And the probabilities that based on the sample size and knowing the standard deviation of the population, that a sample result would vary above or below the mean, what the range that we would expect those means to come out, and what the relationship is to the real population mean. We did that for regular numbers, and we did it for proportions. And now we're looking at, well, how are we going to accommodate for the fact that we don't really ever know the population standard deviation? That's kind of a cheat that we were using, right? And how are we going to deal with that? And that's really something that's really reserved for next week more than anything else. Okay, so I'm going to post, I guess, half